Okay, the exponential functions. So we've done some work on exponential functions. So something like y equals 2 to the power x is an exponential function. And we did quite a bit of work on sketching those as well. The exponential function is y equals e to the power x. It has exactly the same shape, so it's an exponential shape. So we're going round, up, 3, 1. E is an irrational number, a bit like pi is an irrational number. With the exponential function, this has the property that any point on the curve the gradient is equal to the y value. So it's actually the only curve where the gradient of the curve is equal to the value of the function. So for instance here, where y is equal to 1, the gradient will be 1. Where y is equal to 2, if you draw a tangent in here, the gradient here will be 2. When y is 3, the gradient is 3. When y is a half, I'm ruining my sketch now, the gradient here will be a half. When y is a quarter, the gradient will be a quarter. So the gradient is approaching 0 as y approaches 0. So there's a particular number that allows this to happen. There's various proofs of why e is the value it is. I'll let you search them out if you're interested. But e is equal to 2.718 to 3 decimal places. But it's an irrational number, so the decimal places go on forever. You could get it to more decimal places than that on your calculator quite easily. And we'll come back to this when we do second year differentiation, but the value of the function is the same as the gradient. So when you differentiate e to the x, you get e to the x. So that's basically what that statement there is saying. But we won't work on differentiating it just yet. I wanted to do a quick recap on sketching. I don't want this to take too long. So you should be able to sketch these from the work we did on exponentials before. You need to remember e is a number. It's 2.718 to 3 decimal places. So if I want to sketch something like y equals 2e to the 3x, then the 3x will make it a bit steeper. So that power's going to go more quickly. The 2 is a stretch in the y-axis by scale factor 2. So it's going through 2 on the y-axis. Sometimes it's easier to put those in afterwards actually. And it has an exponential shape. So something like that. Y equals e to the minus x. So if x is replaced with minus x, that reflects in the y-axis and it gives you exponential decay. So that one is coming down like so, still going to be 1. E to the power 0 is 1. E to the power 0 is 1 times 2, gives you that y-axis intercept of 2. And then combining all of that together, if you've got something like y equals 5 plus 2e to the minus x. So a bit like you did with the modulus function, you can build these up if it helps. So you could start with 2e to the minus x. So that's a stretch of this one by scale factor 2. And again, it's just getting the correct y-intercept and shape. that we're interested in, and then adding 5 moves the curve up by 5. So you have to pick up the asymptote and move it up by 5. And then it's decay because it's negative x, so it's this one here moved up, so it's going through 7 and down onto the asymptote. So the marks, or to get this correct, you need a correct shape, correct asymptote, correct y-axis intercept. So don't spend too long on this, but if you could just do a few questions just to remind yourself of how those sketches work, and then we can move into natural logarithms.